Before we begin this lesson, we're going to do a couple of quick refreshers. Our first one is going to deal with what happens to the concentration of sodium hydroxide when we take a solution and add water to it. So I want you to take a minute and calculate the pH of a solution formed by adding 10.0 milliliters of 6 molar sodium hydroxide to 500 milliliters of water. Alright, so let's check and see how you did. If we take the molarity times the volume of our original solution, that'll tell us how many moles of sodium hydroxide we're working with. So we have 0.0600 moles of sodium hydroxide, and we're going to add 500 milliliters to the original 10 milliliters of that solution. So our new volume is going to be 510 milliliters. So to calculate our new molarity, we'll take the 0.0600 moles of sodium hydroxide, divide it by the new volume, 0.510 liters, and that's going to give us a new concentration for our sodium hydroxide of 0.118 molar. Now, sodium hydroxide is a strong base, so we know that the concentration of sodium hydroxide originally will equal the concentration of the hydroxide ions in the solution, so our hydroxide ion concentration will be 0.118 molar. If we take the negative log of that number, that's going to give us our pOH, so we get 0.929, and if we subtract that from 14, that'll give us the pH of the solution, which is 13.07. Now let's do another quick review problem. This time we're going to calculate the pH of an acidic buffered solution. So it says calculate the pH of a 0.250 molar formic acid solution that also contains 0.100 molar sodium formate. So go through and do that calculation. We'll be back in a minute and we'll check and see how you did. Alright, so let's see how you did. First thing we're going to do is list the different species that are going to be found in the solution. So we're going to have formic acid, which has a Ka of 1.8 times 10 to the minus 4. We're going to have sodium formate, which 100% dissociates into sodium ions and formate ions. And formate ions has a Kb of 5.56 times 10 to the minus 11. And we've got water, which has a Kw value of 1.0 times 10 to the minus 14. So when we look at our substances, we're going to be starting with our formic acid since it's got the largest of the K values. So we're going to write our dissociation equation for our formic acid, fill in our ice chart, and then write our K expression. We'll plug in X for our hydrogen ion concentration, 0.100 plus X for our formate ion concentration, and 0.250 minus X for our formic acid. We'll assume that our X's are insignificant relative to the initial concentration of our formic acid and our formate ion. Multiply both sides by 0.250. Divide both sides by 0.100, and we're going to get an X value of 4.5 times 10 to the minus 4. That's going to give us the concentration of hydrogen ions. If we take the negative log of that, that'll give us the pH, so 3.35. And we can do our 5% rule by taking 4.5 times 10 to the minus 4, dividing it by the original concentration of 0.250, multiply it by 100, and that gives us 0.18%, so it was okay for us to get rid of our X value. Now we're going to look at a different problem which shows us how buffer solutions actually work. So we're going to calculate the pH of a 0.250 molar formic acid, 0.100 molar sodium formate buffer that we calculated in the last problem after the addition of 10 milliliters of 6 molar sodium hydroxide to the original buffered solution volume of 500 milliliters. And what we're going to want to do is look at this problem in two different parts. The first part's going to be a stoichiometric part where we're going to take our strong base and react it with the component of our buffer until it completely consumes. And then we'll have an equilibrium part, which is the problem like we've just been doing. So first, let's look at our limiting reactant part, our stoichiometry part of the problem. So again, let's list what we have in our new solution. We have the formic acid, and we have the formate ions in our buffer solution. We also have the sodium ions, but that's not going to be part of the problem, so we won't include it. And now we're going to add hydroxide ions to that buffer solution. Now our formic acid has a Ka value of 1.8 times 10 to the minus 4. Our formate ion has a Kb value of 5.56 times 10 to the minus 11. And hydroxide has a Kb value that's very large because we're looking at a strong base. So we're going to start with the strong base. We want to decide what reaction will dominate, and remember that the goal of the acid meeting a base is to neutralize. So we start with our hydroxide ion, and we want to think about what that hydroxide will react with. Well, the hydroxide isn't going to react with the formate ion because they're both bases. So the only other thing in the solution that we're going to be dealing with is the formic acid. Now, strong acids and strong bases react to completion. And we're going to produce water and our formate ion. Now, the issue with this that's different than the problems we've seen before is that we're going to be mixing two solutions together, so we're not going to be able to use molarities in our ice chart. We're going to have to use moles and then convert back to molarity when we're done. So let's do that down on the bottom. We've got moles of formic acid that we need to calculate first. So when we look at that, we had a 0.250 mole solution for every 1 liter. And we have 500 milliliters of it, or 0.500 liters. So that's going to give us 0.125 moles of formic acid originally. So we'll plug that in up here. So we've got 0.125. Now we're going to look at our moles of our formate ion. So we had 0.100 moles for every 1 liter, and our buffer solution is a 0.500 liter solution, so our moles of our formate ion are 0.050 moles. And lastly, we want to look at our moles of our hydroxide ion. The concentration was 6.0 moles for every 1 liter. And we're adding 10 milliliters, or 0.0100 liters, and that's going to give us 0.0600 moles. So let's get that all plugged in here. So this is going to be 0.0600, and this is going to be 0.0500. Now, when we add a strong acid or a strong base to a buffer solution, it reacts to completion. So if we look, our hydroxide ion is going to end up being our limiting reactant. So 0.0600 of it's going to react, and we're going to have none of it left because it's been consumed by our buffer. It's stoichiometric, so 0.0600 moles of formate ion is going to react, which will leave us with 0.065 moles. And we're going to produce 0.060 moles of formate ion, so that's going to give us 0.11. So the last part of this is we're going to calculate some concentrations again, and then we'll move on to part 2. So the concentration of our formic acid after the buffer has completely consumed our hydroxide ion is going to be 0.065 moles in 510 liters. We had 500 milliliters of the original buffer solution, and we're adding 10 milliliters of our strong base to it. So our concentration is going to be 0.127 molar. And we'll do the same thing for our formate ion. So we want the concentration of the formate ion after all of our hydroxide has been consumed. So we've got 0.11 moles in that same 0.510 liter solution. So now we've got a 0.216 molar solution of formate ion. We still have weak acid and the conjugate base in the solution, so there's still components of our buffer left over after it's consumed all of the strong base. So now we're going to go on to the second part of the problem, and in the second part of the problem it becomes just like the problems that we were working on before. It's an equilibrium problem. So we need to think about what we have in our reaction and what our dominant reaction is going to be. So that's going to be our formic acid producing hydrogen ions and formate ions. Now it's in the same solution, so we can use our molarities. So we're going to plug in 0.127 for our molarity of our formate ion. There's no hydrogen yet, but we've got 0.216 of our formate ion. So that's our initial. We're going to have our change and our equilibrium. And since it's a weak acid, only X amount of it's going to dissociate. So now the problem becomes just like the problems that we've seen before. So we're going to get 0.216 plus X of our formate ion. So we've got our Ka is the concentration of hydrogen times the concentration of our formate over the concentration of formic acid. So we'll plug in 1.8 times 10 to the minus 4 X for our hydrogen ion, 0.216 plus X for our formate ion, and 0.127 minus X for our formic acid. We'll assume that these X's are insignificant to make our math a little easier. X will equal 1.06 times 10 to the minus 4, and that's the concentration of our hydrogen ion. Since that equals our hydrogen ion concentration, we can go ahead and figure out our pH. So our pH will equal the negative log of 1.06 times 10 to the minus 4, which is going to give us 3.97. Now let's compare that number to a couple of things. First, go back to where we calculated the pH of the buffer solution all by itself. We calculated that pH to be 3.35. And then we added sodium hydroxide solution to it, and we calculated the sodium hydroxide solution pH to be 13.07. So when we added that 13.07 sodium hydroxide to our buffer, look at what it did to the pH. It only went from 3.35 to 3.97. Buffers are solutions that can resist a change in pH by absorbing excess hydrogen or hydroxide that are added to them.